Okay, hello everyone, and welcome back to the second part of the week 3 lectures. So this is on electricity and generators. Now, divide this up into two parts. So the first part refers to these learning goals, and in the quiz, most of your feedback dealt with the first half of the dealt with the first half of the online lecture today. So this second half is going to be a little shorter. Now, when it comes to electricity basics, there were some of you who mentioned that you haven't really done anything with electricity before. And so one of the questions was, what's the difference between voltage and current? So I'm just going to go through voltage, current, and resistance. So let's start by current because it's probably the easiest one to understand. Current is a measure of the flow of electrons, usually in a wire. In all our cases, we're going to be dealing with the standard setup where there are just electrons in a wire. So the basic entity that we're dealing with in electricity is electrons. Now, electrons, it's a very, very, very small particle. It has a negative charge, and it's that charge that essentially enables electrons in doing everything that they do in electricity. Now, the voltage is a measure of the electrical potential energy of these electrons at a particular point. But just like with gravitational potential energy, it's only really the change in potential energy that matters. So when an electron goes from point A to point B, the potential energy might be high, and then something happens so that at point B, the potential energy is lower. So in the same way that when we're dealing with gravitational potential energy, if there is a potential difference, it means that the electron has lost some potential energy, and that potential energy has been converted into something else. And that something else is basically what the electricity is used for. So it's the conversion of the potential energy of electrons into whatever we want to use the electricity for. That's basically why we have electricity. Now, resistance is the word we use for the friction that electrons experience. And we can think of it as something that converts the electrical potential energy into another form. Most often, we're just referring to thermal energy. So, for example, in a light bulb, there's very high friction or high resistance in the wires in the light bulb. And that's how the electrical energy or electrical potential energy is converted into heat and a bit of light. Now we're going to look at two important equations that relate to voltage, current, resistance, and power, and they are V equals IR. This is also known as Ohm's law, and P equals VI. So that's the power, meaning the energy output per second, is given by the voltage drop times the current that's running. Now, if we know two of the variables, we can solve for the other two. So that's kind of basic mathematics. And just again, make sure that when you solve problems, write down clearly what you know. And then write down clearly how you're going to calculate what you don't know. And it's very useful to draw an image of the situation, either an image or a diagram, to help you figure out what's going on. Now, in this course, we will only look at situations where there's only one power source and there are no branching wires. This is called parallel circuits. So we're not really going deep into electricity. We're just covering the basics that are useful to know for the purpose of this course. Okay, so in the pre-lecture quiz, question 11 was the following. And average car such as a Honda Civic utilizes 60-watt halogen headlight bulbs for high beam. Assume that each headlight is separately connected to the car's 12-volt battery. What's the internal resistance of a halogen headlight bulb? So here, most of you got this right, so I'm not going to go through this one in too much detail, but basically we write down what we know. So we know the voltage, we know the power, and then we can find the current using P equals VI. And we calculate it this way. And once we know I, we can find R using V equals RI, and there we go. However, this question was a bit trickier. A factory requires 45 kilowatts of power. The wires connecting the factory to a nearby power station have a total resistance of 0.80 ohm. How much power is dissipated in the wires if the potential difference between the wires at the entrance to the factory is 240 volts? And then you've been given a hint that as a circuit diagram, you can think of the power station as a battery and the factory as a light bulb. Now, to get an overview of what's really going on here, it's useful to draw a circuit diagram as pointed out. However, one of you mentioned that I can't comprehend a circuit diagram, how to construct one, or how to interpret what it's telling me. So thank you for saying that, because then I will draw the type of basic circuit diagram that we will be using in this course. Now, a circuit diagram essentially shows us the path that the current takes, or the electrons. So we want to, because it's a circuit, it doesn't really have a beginning and an end, but it makes sense to start with where the electricity comes from, or the power generation. So we start with here, the battery. I'm going to draw it as a battery because batteries are easier to understand and more familiar in terms of how we draw them. So let's just draw, we have a battery or whatever, wherever the energy comes from. Then we, no, let me not draw that quite yet. So the energy comes from somewhere, and then we have a factory. I'm going to draw that factory sort of looking a bit like a factory. So here's our factory. It's somewhere else. Now, for the energy to get from the source to the factory, we connect it with wires. So we connected with wires like that. However, we can't just have one wire because we need a circuit. The electrons don't just get dumped somewhere and then we have a whole bunch of useless electrons. The electrons always have to go back to wherever they came from. And so we connect them back up like this. And that's an important point when we deal with electricity, that there's always a circuit. The electrons themselves don't get used up. It's just the potential energy of the electron that gets used up. Or, sorry, not used up, transformed into other forms of energy. So in this diagram here, we've got, now I must admit I've forgotten which end we have the high potential at, but let's say it's over here. So we have high potential over here, so the high, and we have low potential. Generally we call that 0. So we basically used up all the potential energy the electrons had by the time they get back to the beginning. They lose a little bit in the wires, but most of the energy the electrons have is lost in the factory, because that's where we're going to use it. Now, we've been told that the potential difference at the factory, so that's basically between where the wires enter and where they exit the factory, we have a potential difference of 240 volts. And we've also been told, I can write this over here, that the power output of the factory is 45 kilowatts. So what we want to do now is to look at the information we have and say, well, what can I do with that? Because ultimately, let me just put on factory here to specify that. But ultimately, what we want to find is the power loss in the wires. And we've been told that the total resistance of the wires is 0.80 ohms. So we need to do this in 2 steps. So step 1 is to figure out what the current is, because there are no branching wires here. So whatever the current is at the beginning, it's the same the whole way around, because the current can't go anywhere else. So on the next slide, I've prepared the solution. So it looks a bit neater there, but I'm just going to go through the main thinking process here. So basically, step 1 is to find I, and we know that the current through the factory is the same as the current through the wires. And so the current through the factory is P factory divided by V factory, and that's a calculation that requires a calculator. And so now we can find out what I is, and then to find the power loss in the wires, we do step 2, find P wires, which is, so we're going to use an expression that is, it's in a way a shortcut. So we know that P is VI, but we don't really want to calculate what the potential difference across these wires are. But so we use the fact that V is also equal to RI. So V is equal to RI, and then times another I, so we have RI squared. So that's a step that probably is not quite intuitive, and you could have done the calculations, but this is easier. And yeah, that's the thinking, because now we know R for our wire, and we've calculated I. So take a photo of that, and I'll clear this, and then we go to the next page. And yeah, so that's what I did. And then we go through this. So we calculate I for the power station, then for the wires, this is what we wrote down. So I for the power station turns out to be 187.5 amps. And for the wires, the power is 28 kilowatts, or 28,000 watts when we round off to significant figures, which is then the answer that we would put into the question. All right, now note that we don't round off until the final answer, or else we get follow-on rounding errors. Yeah, just a small detail. All right, so question 13 was basically the same question, but now with a different potential difference, because what you found is if we compare this number here, so if we look at that, check the power loss is in comparison with the power used by the factory, the power loss is more than half. Like that's not acceptable. We can't lose that much energy. So the next question is designed to make you go through the calculation again, but this time with a potential difference of 10 kilovolts across the factory. And when we go through the same calculation here, you see that the current that goes through the wires is a lot lower when the potential difference is higher. And that results in a much, much, much smaller power loss in the wires. So now the power loss in the wires is negligible compared to the power used by the factory. And that's what's important here. And this is essentially the explanation for why we have high voltage in transmission lines. It's because the higher the voltage, the lower the energy loss due to resistance in the wires. And one of you asked whether there's anything we can do except use high voltage to avoid power loss in wires. And no, the main thing is really to keep the voltage high, but also obviously to have as little resistance as possible in the wires. But in reality, it's impossible to have zero resistance in those wires because the wires are made of something and they're kept roughly at normal temperatures because they're outside. All right, there was also a question about step-down transformer. Now, most of you did this correctly, so I'm not going to spend too much time on it. But just as a reminder, we're talking about a step-down transformer in a certain substation that converts incoming 132 kilovolts to 11 kilovolts. That's quite a common step-down process in a transformer. If the primary coil has 180 windings, how many does the secondary coil have? So again, we write down the relevant relationship, we write down what we know, and we plug it in. Now notice that we don't have to convert the units here into just volt to stick in SI units. We can keep them as kilovolts, but as long as we keep the units in our equation, we just do the calculations with those units. And now we see that kilovolts divided by kilovolts, well, that's just one, so they disappear. And then we have no unit troubles. However, if we'd had kilovolts here and let's say just volts there, then we would have seen in our equation that we can't take kilovolts divided by volts. Then we can only take volts divided by volts, and we would have been left with kilo, which is the same as 10 to the power of 3. So if you didn't follow that, don't worry too much. Just make sure that you keep your units in your calculations. So the answer is that we have 15 windings on the secondary coil. Now, someone asked, what source of energy do they use to step up voltage? And I'm glad you asked that, because it's quite important to point out that transformers don't require an energy source to either step up or step down voltage. In transformers, in many ways, it's quite a simple situation where the power in equals the power out. If I go back to the diagram on the previous page, see here that the transformer really only consists of 3 things. We have this thing here, which is a metallic core. It's usually made of iron. So it's just 4 iron blocks that are put together into a square. Then we have the windings on the primary coil, and we have the windings on the secondary coil. That's it. And someone else commented that, I think it was for transformers, that we may, like, whether we understand how they work. We do understand how they work. And they basically work because, and if you don't follow this, that's okay. This is not part of the curriculum, but just for those who are curious, it works because the first coil sets up a magnetic field that goes in a loop through that metallic core, through that iron core. And so basically whatever happens on the left-hand side here in the primary core, that is transmitted to the secondary coil through this magnetic field loop. So that's how it works. But we don't really cover magnetic fields in detail in this course. So it's cool, It's really interesting physics, but you don't need to know this for this course. All right, so that's basically an explanation of why we don't require an energy source. All this does is that it takes the certain power that comes in and it spits out that power on the other side. But the power, as we've seen, remember, power is equal to V times I. So all a transformer does is that it changes, in a sense, how the power is transmitted. So if it steps up the voltage, it steps down the current, but the product of the two is always the same. So that's what it says here. All right, now if somebody wants more practice problems to work with this, there are the practice problems provided on the Moodle site down in the practice problem section, but here are also some links to other places where you can find practice problems if you are interested. All right, so moving on to the second part on generators, co- and tri-generation plants, and energy grids. Now, when it comes to generators, one of the changes that was made from last year was that we know that generators can be quite tricky to understand, but also that the best way to learn about a generator is to kind of play around with one. Obviously, we can't do that now that you're all at home. And so we designed a completely new online lab this year to help you learn about generators and motors. So in week 4, you'll do a lab on generators and motors, which will help you understand these concepts better. However, if you would like to explore generators and motors a bit more now, then the following simulation is useful. This is, by the way, also the simulation you'll be using for next week's lab. So if you go to fetcolorado.edu, you can go to play with simulations, physics, electricity, magnets, and circuits, and then down to generators. Let's see if we use green. Yeah, generators down here. So you can get a head start if you would like. And to guide your exploration, here are some of the questions. And some of these questions you're going to be answering anyway in the lab. Now, more on generators. You had 2 questions in the pre-work on generators, and for the most part, you did very well. In question 15, you were asked which of the following is not an essential component of a generator, and most of you knew that heat sources are not an essential component of a generator. What a generator does have to have is a wire in the closed loop, a magnet, and something that rotates the magnet relative to the wire. This is what we call the turbine. And note that they just have to rotate relative to each other. So whether it's the magnet or the wire that's rotating, either of those will work when you build a generator. And different generators have solved that problem in different ways. So if you look at a generator, you might see a rotating magnet or you might see a rotating wire. Now, electricity is induced or created. So whenever we say that electricity is created, we know that because of the first law of thermodynamics, conservation of energy, it means that energy has been transferred from somewhere else. And in a generator, it's the mechanical energy of rotation that is being converted into the electrical potential energy that is what we call electrical energy. And note that electricity is induced in the wire when the magnetic field, because of the magnet, through that wire loop changes. So that deals with question 2, where the question was electricity is induced in a wire when, and all of you knew that if you just rotate a wire, then nothing really happens. But there must be a magnetic field involved. And that magnetic field, it's not enough that the magnetic field passes through the wire loop. The magnetic field through the wire loop must be changing. That's when we create that's when we have a generator. And the simple explanation for that would be, if all we needed was a magnetic field through a wire. So let me just draw that situation. How would I draw that? So, okay. If I have sort of a wire loop here, and I have a magnet over here with a north and a south pole, then we've got the magnetic field coming out. So kind of magnetic field lines coming out. Some of those magnetic field lines go through that wire loop. Now, if nothing changes, if this is just a stationary situation with magnetic field going through a wire loop, then nothing moving. So there is no there's no motion here. If this created a current, then we would essentially be creating energy from nothing. Because when we have transformation of energy, well, it needs to be taken away from someplace and being put into somewhere else. So when we are inducing electricity, then we are putting energy into electrons, but we have to take it from somewhere else. So if this wire here, if this magnet were rotating, now what we're doing is that we're taking some of that rotational mechanical energy from the magnet and putting it into electrical energy in the wire. And that's why there has to be motion involved for generating electricity. So the next step to ask now is, well, in generators, what is it that drives the turbine or the thing that generates the motion? And that's where we get into power stations, because there are so many different ways we can get a turbine to move or to rotate. So for example, in a coal-fired power plant, we have a steam engine. And in this case, the water or water turns into steam inside that heat engine is being heated externally by a boiler, and that runs on coal. So that's one way of getting a generator to rotate. That it's essentially the steam pushing past the turbine that forces it to move around. We can also get a turbine to rotate in a nuclear power plant, which works in a very similar way to how a coal-fired power plant works. But there are other ways as well that are more environmentally friendly. So in a hydroelectric dam, what we've got is that we've got water at a high point, so high potential energy, and water that can flow down to a place of lower potential energy. And as it flows down, it rotates turbines inside that place where it can flow. So inside the tunnel or the pipes where it flows through. So that's another way of getting rotational motion. And the last one I'm going to mention is wind turbines. So when we get wind power, that comes from the wind forcing blades to rotate. Those blades are connected to a generator, but here it's literally those blades that are forcing the rotation and connecting that to a generator where the rotating blades are causing a magnet or a wire to rotate and thereby inducing energy. So, generators that are powered by fossil fuels, and we're going to look more at fossil fuels next week, They are heat engines. And so this is how the heat engines that we've talked about this week is connected to the fossil fuels that we're going to look at next week. And like all heat engines, they operate between two temperatures. And as we've learned, due to the second law of thermodynamics, there will always be some energy loss to the cold reservoir. Because remember that a heat engine operates between a hot and a cold reservoir. And note that the fluid in the cold reservoir can still be quite hot in terms of our definitions. The only reason why we call it the cold reservoir is that it's colder than the hot reservoir. So as an example, in this diagram here of the steam engine that we find in a coal-fired power plant, the hot reservoir is basically the temperature of the hot steam. The cold reservoir is the water that's been cooled. And the engine is the device that converts some of that heat into work. And note, some heat will always spill into the cold reservoir. And again, notice this conservation of energy. I know that I've said this before, but I'll say it again because it takes a little while to get used to these signs. All right, now, cogeneration plants are basically, so if I go back to this thing, I've said a couple of times that this cold reservoir, this one, can operate at relatively high temperatures. That's what a cogeneration plant and a trigeneration plant make use of. So instead of this just being waste heat, it's further making use of that energy dumped into the cold reservoir. And that's why co and trigeneration plants are more efficient than traditional power plants. So if we go here, we see that for a cogeneration plant, we get some fuel loss, or some energy loss just to the environment. That's unavoidable. A certain amount is converted to electricity, but then the heat that's left over, that heat can still be at somewhere between 50 and almost 100 degrees. Now that's at an excellent temperature for general space heating. And so that's turned into just put into the central heating system of the building that it's in, or you can do remote heating. Now this here is just a comparison of how much more fuel we would have to use if we were to create that electricity and heat separately instead of doing both in a cogeneration plant. So to get the same effect, to generate a certain amount of electricity and a certain amount of space heating, if we have separate power production, we need 158% fuel. Whereas if we do this in a cogeneration plant, we get it for the equivalent of 100% fuel. So we need almost 1.6 times more if we do it in separate power production. So that's quite powerful. It shows how valuable it can be to use a cogeneration plant. Now, a trigeneration plant takes this even further. So a trigeneration plant, first, it generally uses natural gas to produce electricity, but then the spill water, so what's thrown into that cold reservoir, that is used for heat, so just hot water that can be circulated throughout the building to heat up the building. But in addition, trigeneration plants have something called an absorption chiller. And that essentially it's creating cold water in a process that's similar to the refrigeration process that we looked at in part 1 of the online lecture for today. So that's why it's called tri-generation plant, because it does 1, 2, 3 things, whereas a cogeneration plant only does the first 2. Now notice that if you have an absorption chiller installed, you can run your plant as a tri-generation plant, but you can also decide to just sort of shut off the tri-generation plant, in which case you are essentially running your plant as a cogeneration plant. So this is in response to that other question in the pre-lecture quiz, which is whether you can switch one to turn into the other. And this is the reason why you can turn a tri-generation plant into a cogeneration plant, but not the other way around. So a lot of you answered that correctly, but there were also quite a few who said that co and tri-generation plants generate more heat than regular power plants. So that's not correct. They generate about the same amount of heat, but the difference is that co and tri-generation plants use that waste heat for something more useful instead of just it being waste heat. Oops, sorry. So just to summarize, tri-generation plants can be switched to run as cogeneration plants by simply turning off the absorption chiller. A cogeneration plant does not have an absorption chiller installed and therefore can't be turned into a tri-generation plant. And lastly, both of them have higher efficiencies than regular power plants because they're turning that waste heat into useful energy. Because remember that efficiency is a measure of how much useful energy are you getting out of the total energy you put in. So one of you asked a very good question. That's why are co and tri-generation generators not popular? Well, I wouldn't say it's that they're not popular. It's more that co and tri-generation plants are quite extensive systems that must be built into the building. Because remember that in a cogeneration plant, the waste heat has to be turned into some form of space heating to be useful elsewhere in the building. And that means that there has to be some infrastructure in place to move that waste heat, often through hot water, to all of the other places in the building. And that's not trivial. It's not impossible, but it requires a bit of effort to set that up. And so it can be challenging to retrofit an old building with co and tri-generation plants. So that's why we mostly see them in newer buildings. And a very good example is the Tyree building on the UNSW campus. So that was built with a tri-generation plant and also with solar panels on the roof. So it's quite an amazing energy sustainability building. So getting to near the end now, we're going to look at the movement of electrical energy around the country. Well, I say the country, but really, if you look at this map here, we have the Northern Territory and WA is not featured on it. And the reason for that is that they're just too far away. So we always have some power loss when we transfer energy from one place to another. And so the further we have to transfer it, the more energy loss we're going to have. So it comes to a point where it's just not worthwhile anymore to transmit it any further. So this is the reason why Australia as a whole doesn't have one cohesive power grid. However, the power grid we do have, it's called the National Electricity Market, is one of the biggest ones in the world. As if you look at it, it spans a very long way, all the way from quite high up in Queensland down to Tassie. So transmission lines cover very long distances and they have very high voltage. so that we can reduce power loss. And we already looked at why high voltage is useful to reduce power loss. By transmitting electrical power at very high voltages, the current is very small because P is equal to VI, and that's what minimizes the power loss. And so just to specify, in typical wires used in the transmission grid, we have resistances of around 0.023 ohms per kilometers. That's a very, very low resistance. This is really good. But when we transmit electrical energy across thousands of kilometers, it still becomes noticeable. So another good question coming in today: how long would it take electricity from the bottom border of New South Wales to reach the top border of New South Wales if you used a 500 kilovolt transmission line? This is almost like a trick question, because that's not quite how electricity grids work. So to exemplify, think of electrons in a wire as sort of identical balls in a full tube. If you push a new ball in at one end, so if we were to push a new ball in at this end, the effect would be that this ball here would instantly fall out on the other end. So there wouldn't be a time delay. It's not really the new ball that comes out at the other end. That's going to take a very long time. But still, the effect in terms of energy flow is instantaneous. We put one ball in at the bottom of New South Wales, and immediately another ball, meaning another electron, falls out at the northern end of New South Wales. So in summary, it's the electricity or the energy moves instantaneously from one end to the other, but the electrons don't move very much at all. Now add to this that we actually use AC, so alternating current. And what alternating current really means is that the electrons aren't sort of drifting along in one direction. They just jiggle back and forth. So let's say this electron here, all that does is jiggle back and forth and back and forth and back and forth. And that is how an alternating current works. So lastly, we look at the whole sequence from electricity generation to usage. So we start off with generation at a power plant. Then we transform that electricity to high voltage, low current. Then we transmit that through what we call transmission lines. So the majority of the distance covered is done through transmission lines. Once we get to sort of a regional area, this might be a particular suburb or a particular town, then we have a substation that we use to transform the voltage down again. So that's a step down transformer. Then we use what we call distribution grids to just distribute that energy locally. So that has higher losses, but because we're only distributing the energy across relatively small distances, the total effect is not as severe. And then it gets to our home. Now, the question about that in the pre-work, oh, sorry, this is not question 4. I think this was question 17. So the correct answer here is that distribution and transmission networks are connected at substations. So we see here, transmission and distribution networks, they are connected at the substation. Why are the other ones wrong? Well, for the first one, distribution networks have higher voltages than transmission networks. No, it's the other way around. So transmission networks have high voltage, distribution have relatively low voltage, at least lower than the transmission grids. Distribution networks are mostly rural, whereas transmission networks are closer to the end user. Again, those are switched around. The transmission lines is what we find, I guess, generally rurally, away from the cities. And then we have the distribution in the areas where people actually live. And lastly, substations contain step-up transformers. No, a substation contains a step-down transformer. And to finish off, I wanted to address just one more question from one of you, which is that theoretically, could a substation be switched to stepped-up transformers? Obviously, they wouldn't do this in practice. Well, yes, you are quite right. So here we have an image of a step-down transformer, but all we have to do to turn this into a step-up transformer is to send the energy the other way. So notice that there's 2000 watts, well, in this example, 2000 watts going in, 2000 watts coming out. So we would just reverse this process and send electricity this way, and then turn it into a step-up transformer. So very good question. It's really, really informative to see all of your questions. So make sure you keep them coming. It's also the easiest marks you get in the quizzes. And with that, I will finish off this part 2 of the lecture, and I'll see you all for the session later today.